Imperative that you do read those comments. If you can't read them, you have to come see me and I'll explain what they are, okay? You're going to have part 2 of this assignment given to you tomorrow. It'll be a similar type of approach, except this time the logs you're going to get are going to be gamma ray logs, and you'll be correlating yet another line doing the same thing, okay? So make sure everything's done tomorrow. Be on schedule with everything because, as I said, each one of these components is going to involve yet another step in the process of actually being able to evaluate the potential for a play, okay, or in this case, exploiting a known oil field, all right? Does anybody have any just broad questions about the exercises so far? I have had several people come up to me saying like they needed copies of the logs again because they did something they probably in hindsight should not have done. If you need copies of the logs are available. You have to photocopy them yourself. Get Sherelle to do it for you downstairs because today's a kind of an intense day for me, so you may not find me when you need them, okay? And for God's sakes, as I said, don't leave this at the last minute because you're not going to like it if you leave it at the last minute, all right?
You want us to color over the log?
I'll leave that entirely up to you. Okay, in terms of aesthetics, you have to decide what's going to look best on this. I've seen a couple logs so far that have been reasonable, not necessarily correct, but reasonable in terms of how they were done. So, as I said, I'm looking for both the right interpretations as well as a certain amount of aesthetic attractiveness that's going to make it the type of thing that you want to see. Okay. And again, a reminder that you follow the rules for petroleum geology. Do not follow the rules that you got in stratigraphy because those are not directly applicable for this project. Okay, and I've warned as many people as I can about that. Okay. Other questions? Okay. Well, I guess we might as well get started out. Before we finish off for here, as you know, we did not have a lecture yet for Monday. I am working on getting an online lecture for you. If you look online, you see I modified the lectures a little bit. Today's lecture was supposed to be talking about online well logging services, and I decided that, frankly, I don't know anything about this. When it comes down to it, I've never worked in the well logging business, so why would I be the type of person to give you some discussion about this? So instead, what I did was I contacted a student of ours who up until recently was working for Schlumberger. And I asked if he'd be willing to do an online interview. And we are arranging that now. And if it works, I'm trying to figure out a way we can do this in Skype and record it as an actual face-to-face recording. If this works, this will be something that we can do for a lot of other lectures here. Because I would love to actually talk to somebody in the oil industry from his office in Houston or her office in Houston saying, like, here's what I'm doing, here's what my office looks like, here's my boss, here's my coffee cup. I don't care, as long as it's useful stuff in terms of information for you. Okay, so this, I think, opens up the potential for a lot more diversity in terms of how we actually do things. That lecture will be online as soon as possible. I'll let you know when it's going to be online, and you can access it at your earliest convenience, okay? All right. Lights off. We're going to talk today about, well, same thing we've been talking about all along, some more well logs. This time we're going to be talking about the so-called porosity logs. Well, 2 of the 3 porosity logs, neutron and density logs. Now before we do this, and this is going to be one of those annoying days where I'm going to be switching back and forth between lights being on and lights being off. And Diane, thank you very much for agreeing to film when the lights are on, because what I want to do is I actually want to start using the chalkboard to show you how log response works. I'm not entirely convinced that any of you are actually paying attention to anything I'm saying. And I'm not entirely convinced that any PowerPoint presentation is effective at teaching you stuff. So I figure if I'm doing stuff on the chalkboard, which will not be available in any other source, then you'll have to keep up with me and make notes at that point, okay? And I strongly encourage you to do so. If you're going to understand how log responses work for rocks, it's always often be drawing them while we're talking about those very log responses. Now before we do that, let's talk about what we did last time. We were talking about radioactive decay types, gamma ray emissions, and gamma ray logs. Nice, simple, tight little lecture. Really didn't go into much detail because this particular log is fairly easy to actually explain and understand once you get through the basic stuff about radioactive decay. And again, this is not particularly new to any geology major. You're aware that there are naturally occurring radioactive minerals. Sometimes it staggers people about how much radioactivity there is out in the real world. I mean, you walk by a granite minutes, then you have the potential for getting a little bit of radioactive charge. But mind you, that pales in comparison to flying in an airplane. All right, it's been demonstrated time and time again that people that regularly fly at high altitude, like pilots and stewardesses, are exposed to more cosmic radiation than they would ever care to imagine. In fact, they do have higher incidences of some of the radioactive-related cancers and all. So the stuff is all around us. And if you're going to be a geologist, it's always a good idea to take advantage of what's around you to do a better interpretation for the subsurface. So it's important that you realize that there are three types of radioactive decay. Alpha, which is the loss of an alpha particle, which is why it gets its name, alpha decay. The alpha particle is just basically a stripped down helium, a helium nucleus if you wish. There's beta decay, where you lose a beta particle, which in this case is an electron. And that one's kind of weird. I mean, you have to wonder how some of this stuff actually happens. It's driven by physical laws. But for a neutron to just decide that it doesn't want to be a neutron anymore and just kind of kick out an electron and turn into a proton, that's kind of weird. That's like somebody all of a sudden decide they don't want to be male anymore or female anymore, and they just kind of kick out a body part that they don't need anymore and all of a sudden change their sex. It's just doesn't seem natural, but it is. And then gamma decay, of course, is where you actually capture one of those electrons and do the opposite conversion, okay? Gamma rays are emitted in all types of these decays, and ultimately that's what we're going to be recording through the gamma ray logging devices. One of the nice things that is not done all that effectively in the petroleum industry, because ultimately they don't care. And again, I mean, a lot of times you hear people talking about how, you know, they should do more, they should advance academia, that they should make all this stuff aware so we can understand the Earth processes a little bit better. Well, they actually do contribute an awful lot to basic research, but frankly, who cares when ultimately what you're trying to do is get more oil and gas out of the ground? Remember, these guys are driven by profit, and there's nothing wrong with that. That's just the way our economy runs. However, if they were to go into a little bit more detail, they could actually start determining which elements are responsible for the gamma rays that are being detected, because each of these radioactive elements gives off a slightly different frequency of gamma radiation, or energy levels. Not frequency is the wrong term. Energy levels is what I meant to say. As I said, in the oil industry, we don't care. We just look at the bulk component of it, because all of these things are largely associated with shale beds. And then I gave you this god-awful diagram here with all the text. And again, the reason for the text-heavy PowerPoint slides is when you are actually studying, you know, getting ready for exams or something like that, you can go back to the slides and read up on them and anything you happen to miss. But I don't expect anybody to be reading these as they're being presented. The main thing to know is that gamma ray logs are often called shale indicators because, again, most gamma rays are trapped associated with the shale components. With those ringers, don't forget, if you have an arcosic sandstone, that can have an incredible amount of potassium-40 in it, giving you very high gamma radiation. All right, and this is where I left off with talking about this whole thing, because, again, one of the things when you get into using logs is to get so dependent upon one type of log that you miss the beauty of how all this information can help you to do a lot more interpretation of rock units. All right, you really need to have multiple types of logs working in conjunction with one another to make determinations about not only what kind of rocks you're dealing with, but ultimately the characteristics of the formations that you're encountering, which is what we're going to get into today. In fact, for the first time, we're actually going to start talking about how you can use logs to look for specific types of fluids. And in particular today, it'll be natural gas. Okay? Now here's today's agenda. We're going to be talking about the porosity logs, or two of the three porosity logs. We're leaving one for later on. Those two logs are the neutron log and the density log. When we talk about these, we're going to go in a little bit more detail than we did with the gamma ray logs, because these are a little bit more technical in what they're doing. And the reasons for how they work are a little bit more based upon chemical parameters. Gamma radiation is easy to understand. Resistivity is easy to understand. But these are a little bit more intuitive. So you have to think through what it is they're actually telling you and make determinations based upon those data. And as always, you have to exercise a little bit of caution, because every once in a while the interpretations you make are wrong for some reason. Okay, so never, ever, ever rely entirely on one log, but understand that they have the potential to give you very useful information. All right, let's talk about this. Now, these are the porosity logs. And porosity, as you should realize, is one of the major parameters that you want to be able to determine when you're doing petroleum reservoir characterization. That's why we did that first lab, looking down a microscope, so you could understand that rocks contain holes, and those holes are where the fluids are going to be contained. But the problem is, trying to establish just how much porosity is in the subsurface is not the easiest thing out there. That's the real issue. There are logs that can tell you something about water, for example, resistivity does, and there are some times that you can actually use the amount of resistivity to record the amount of water and hence the amount of porosity. But since resistivity is controlled by variables like salinity, that doesn't always give you useful information. When you see changes, it doesn't necessarily mean the porosity is changing, it means the water is changing. So that's not directly useful if you're dealing with issues about porosity. We need something else. Hence the so-called porosity logs, of which there are 3. Now the name refers to the neutron, density, and sonic logs. We're going to leave the sonic log until the next time we meet in lecture mode. Okay, so don't worry about that one for today. The neutron and density sonde is more or less part of the whole well logging apparatus. In this case, there's the porosity sonde where it's got the ingredients kind of built up into it. There's other components, and we've talked about these long suppository type things where each one of the modules is doing something different. Okay. Now, what we're going to do today is we're going to talk about the neutron log first, and then we're going to talk about the density log. And as I said, here we're going to have to turn the lights on and off a little bit because I want to give you the basics for how these work, but then I want to come back and show you how the responses work and how you can interpret certain aspects of reservoir characteristics if you're clever in your interpretations. So here's the neutron log to start with, okay? The way these work is they are emitters. They have got a radioactive source. In this case, it's tritium, I believe. That's what I've heard. Although tritium's I always thought was kind of like a liquid component. But this is what I read up somewhere, was it was a tritium source. It generates neutrons. That's the key thing here and why it's called the neutron log. So you have an emitter that's at the base of the sonde that is emitting neutrons into the rocks as you're pulling it from the base of the well up to the top. Okay? These neutrons will pass into the rock. And if they encounter nuclei of a similar weight, they will be absorbed. Now, because it is a tritium source, the neutrons that it is most susceptible to will be those associated with hydrogen. So if you wish, this can almost be viewed as a hydrogen indicator. But I'll show you how it is used in terms of establishing porosity based upon certain important parameters. The diagram you see here basically is one of those sondes, and here they're talking about the source as being a 16 Curie, whatever the heck that is. I mean, I don't deal with this. This is the technical side of things. I will tell you this, that as a radioactive source, and a highly radioactive source, this is one of those things that has all sorts of very, very strict restrictions on it. All right, so when you're driving by a Schlumberger truck down the road, you will see radioactive symbols on all sides of it, and it's the type of thing that you have to have a lot of respect for, okay, because this is not like a slightly radioactive granite. This is the type of thing that will fry your genitals if you get too close to it. So making sure that this is carefully shielded is a very important component of the whole technical side of things. The thing also to note is that this is a very shallow penetration type of approach. It only goes in about 6 inches from the well, so 6 inches into the rock, about like so. It usually picks up primarily the zone that has been impacted by the mud filtrate as well as residual hydrocarbons. So it's not going to be virgin formation. It's going to be the part that has already been affected by the actual drilling process. However, it doesn't really matter because that can still be used to determine the hydrogen concentration of what is in the rocks. And as I said earlier, the more hydrogen you've got, the more absorption. Right? And that's an important thing. That's the one thing you have to remember about these particular logs. High counts indicate low absorption, which is interpreted as being low porosity for the most part. High counts equals low absorption, low porosity. Low counts means high absorption, high porosity. All right, that's where this interpretation comes from. Okay, don't worry too much about that aspect of things, because really what's important is not the counts as it is what it all means. This is the stuff that you really want to be aware of. So this is the stuff you start writing down now. Number one, shales absorb neutrons because of the high water content. Water contains hydrogen. All right? Therefore, water will be absorbing neutrons quite effectively. Number two, water and oil have similar hydrogen content. So they behave similar on these logs. Okay? So in other words, you can't really tell the difference between oil and water. And by the way, if it's not already apparent, it's the water that's doing the absorptions, not the salt, not the salinity. So salinity is not a variable here. And I hope you can see also that if you were to run a neutron log in conjunction with a resistivity log, you can start to tell which waters are saline and which waters are not saline. You follow? Because oil ultimately is not saline. So if you start seeing resistivity kicks, but the neutron activation being the same, you start thinking salinity differences. Very important consideration for resolving fluids. Number three, gas has ultimately very low hydrogen content. I'm still trying to stomach this one, because I'm thinking CH4, 4 hydrogens per carbon, H2O, 2 hydrogens per water. But overall, I guess in terms of overall weight or so, it tends to be considered to have low hydrogen given the amount of carbon you have attached with it. And lastly, coal is the ringer. Coal absorbs neutrons like friggin' crazy, which means it's going to give you really, really, really strange kicks. So beware of coals. Although in some cases coals are not bad, because if you have a lot of coal, there's a potential for having natural gas as well. But of course, not oil. Why not oil for the most part? It's the wrong kerogen types. Remember, we talked about sources of organics as well. Okay. Now here's the log, and I'm going to read this for you here now and leave it up while we talk a little bit about the actual responses. Okay, so let's just talk ourselves through this, and then we're going to go to the chalkboard here, and you're going to have to get ready on the camera. All right. All right. So number one, neutron logs measure the porosity of a formation, indicating the quantity of hydrogen, etc. It is calibrated to limestone. That is, we just have to have some sort of a base of calibration. So it normally is calibrated to limestone, and you'll often see up here, or they have the lime line here, what they often will say is limestone equivalent units, LEUs. So when you see the information up here, it's based on porosity, going from 0 to 30 or 40%. That minus 10 component there, you can't have negative 10% porosity. That, because you're basically dealing with a numbered response, that allows you to actually look for any drift or any potential errors and stuff. Okay, so this is all, as I said, is related to limestone. It's usually called the compensated neutron porosity because it is evaluated or basically established against limestone. Okay. Using API, neutron pin. I don't know what that means, and frankly, you don't have to worry about it either, okay? All right, so this is basically what we're dealing with. There's a neutron response log. You've seen this diagram previously. This is a sandstone indicator. I'll come back and talk a little bit about what this all means a little bit later. But for now, I think the best way of dealing with this is to do a quick and dirty cartoon of some of the responses that you need to be aware of for the logs, showing you how they all work together. So everybody blink for a second. Already drawing this when I was doing it. For those of you that did not, keep up. Let's talk first of all about a sequence like this, where we've got a layer of sandstone overlaying shale, overlaying coal, a tight limestone, meaning a non-porous limestone, a porous limestone, shale, and a gas-bearing limestone. I'm going to draw for you the SP log response, not because we actually need it today, but because, frankly, it's the one log we haven't been spending a lot of time on, so at least you'll be able to relate how SP characterization should work with lithology. Then gamma ray resistivity, and lastly, the neutron porosity. In fact, actually, yeah, we'll do that one last just for the heck of it, okay? Now, for SP response, you probably are going to see something that looks like this. The coal isn't going to kick very much in terms of SP response, nor will the limestone too much. So, in other words, you're probably going to get a response that looks more like this for SP characterization. The kick you're going to see primarily is going to be with sandstones because of water content, and in this case probably salinity, all right? Now, talking about the gamma ray logs, for gamma ray you'd expect to see the shift towards the right side of the diagram because of the shale. Coals usually have a pretty significant kick as well, even more so than the shale. Sometimes they come right back on the other side. And remember, when you're dealing with resistivity, this is a logarithmic scale. Sometimes it goes off scale relative to what you're dealing with. You'd have to literally physically add this to the other side to figure out where the scale would be. Comes back in this direction. Limestones tend not to really care too much. Shale kicks back in that direction. That's the type of response that you're going to get. Now, if you look at this, you're not going to be able to tell very much difference between sandstones and limestones because in terms of resistivity, they're composed of non-resistant minerals. All right? Whether or not they contain water in them, saline water, is irrelevant at this point, although you can use the resistivity to tell you the differences there. Okay? Now, because I am going to overlap things, I think I will use a different color here. I think green is good for resistivity. All right, so resistivity looking something like this. Porous limes are going to kick way up like this, and then like so. Now, this is the issue you get when you're overlapping logs. You've got to be able, literally, to be able to look at the log responses and see where they are actually dealing, or where they're overlapping. So, for example, this interval here, which shows you the shale, there's your resistivity kick versus your gamma ray kick. Okay, so you see here the resistivity shifting this direction versus gamma ray. For the coal, there's not much difference overall. For the limestone, you get a kick back in this direction. Okay, you get the idea that you can look at how formations behave if you can look at this in terms of packages or carpet. I'm trying to think of the word I want to use here. Individual packages, one layer at a time. And in fact, in the oil industry, it's not unusual to see people kind of just blowing up that area, looking at the characterization, because you can get the numbers off this to enter into various formulas for determining things like salinity. Now let's add the neutron porosity, the first new log that we've dealt with so far. Okay? Now, in the case of this is where you're going to start getting components which are going to be able to tell you something about either porosity or apparent porosity. Okay? Just let me draw this here first, and then we can talk about what it all means. Now, notice the kicks, okay? There's your apparent porosity of 0%, there's 40%. Do shales have 30%, 40% porosity in them? I mean, they may, but no real permeability. The kick here is due to the fact that shales absorb neutrons. Remember, absorption of neutrons gives us an indication of porosity, but only if the lithology is going to be acceptable for doing that. Look at the coal. Again, kicking way off on the side here. Because, again, coal absorbs neutrons like crazy. Coals do not have 90% porosity in them. All right? They just have the materials that are capable of absorbing the hydrogens or the neutrons that give you the appearance that there's porosity. So simply doing a one-on-one interpretation of what the porosity is based upon the responses is wrong. You have to know the lithology. And how do you know the lithology? You don't have this. That's your interpretation. What you've got is an SP log, you've got a gamma ray log, you've got a resistivity log. You try to determine what the likely lithologies are based upon this, and then the neutron component of it can be used for things that are relatively useful. Now notice, for the first time, we're starting to talk about things like tight limestones versus porous limestones versus things like gas-bearing limestones. If you know your formation type, if you know the lithology, you can actually start making determinations as to what type of porosity you've actually got. if this is, for example, all limestone, the kick that you see here going in this direction, 20% porosity, all of a sudden down to here where you start seeing things like 20 and 30 and 40%, or 20 and 30% porosity, that's a shale obviously, indicates that you're starting to get into a rock that has got more holes. If this is limestone, continuous limestone, the neutron response tells you something about the nature of the porosity. So this might not be a bad place for you to consider drilling if you think that the fluids that are in that rock are actually going to be containing natural gas or oil. But here's where you also have to consider the resistivity. Okay? If the resistivity is really off the scale in this direction, there's a good chance it's not going to be oil. It's going to be instead salt water. All right? So you give that a miss. But look down here, okay? There's another limestone. You have porosity that indicates very little porosity at all. In fact, it may not be that there's no porosity. It may just be that what you have here is a potential gas-bearing zone. Potential, because you don't really have enough information yet. Why? Because natural gas does not absorb neutrons as much as you would expect. You get this shift going off in the other direction of an apparent lack of porosity. Now, I have to warn you, there is no way that you can judge on the basis of this alone whether this is gas or a tight limestone. But in conjunction with other logs, you can have that potential. We're going to talk about something in just a few minutes called crossover, involving not only the neutron logs, but also the next log we're dealing with, the density logs. That's one of those magic little secret things that petroleum geologists look for, and looking for potential gas deposits. Not necessarily oil, because oil behaves like water. Oil is a little bit more difficult to address in something like this. All right? Now, has everybody had enough time to draw this? That's doing it? All right. If you could kill the camera now, we'll go back into present. And again, sorry for the lights going on and off, but that's one of the perils of using PowerPoint these days. All right, so neutron logs can be used to resolve not only porosity, but lithology when they're done in combination with other logs, including the density log. And speaking of which, let's talk about density logs. Now, here's the density logs. This cartoon sketch you see on the left gives you an idea of the basic components of what the density logs actually look like. And this one you see here is, I got this off a site that's called Free Patents Online. So I guess you can make your own density sonde if you wanted to, just following the different components, if you knew what all these different numbers were. Basically what you have here is a gamma ray emitter, a source, attached to a skid plate. And what the gamma rays are doing in this case is, again, sending off radiation into the rocks. And you have two detectors. One is a near detector and one's a far detector. This gives you an ability to do shallow penetration and deep penetration. So once again, we have another radioactive source. But this is not an emitter of neutrons. This is an emitter of basically beta particles, okay? Gamma particles. Here's the reasoning behind how this all works, okay? And this is a chemistry-driven idea. The gamma rays interact with electrons in the rocks, or clouds of electrons, if you wish, okay, that are in the formation. It doesn't really matter what the source is of the electrons in this time. It does not have to be a hydrogen electron. Electrons are just electrons. But the idea is that the response you're going to get is going to decrease. The flux is going to decrease with the more electrons that your source of radiation is encountering. All right? Or if you look at it from the point of view of a standard chemistry 100 approach to things, the number of electrons is equal to the number of protons in a substance. That's the Z or Z component of things. And the atomic number is equal to the number of protons plus neutrons. All right? If you assume that on average that the number of protons is going to be half the number of the atomic number, all right, and that's assuming that you're going to have one neutron for every proton. It's not always accurate, but it's pretty close to it. All right? You can estimate the apparent formation density What it means is if you have more electrons that you're encountering, you have a more dense substance. It's not a one-to-one relationship. It's not entirely correct. And a chemist would argue, but what if you have a big chunk of uranium in the middle of this? It's going to throw your signal all over the place. To which a geologist in the petroleum industry would argue, you don't get big chunks of uranium. In the subsurface, when you're dealing with sedimentary rocks, what do you get? You get calcite, you get quartz, you get clay minerals. Those things have different densities because they're composed of different elements, but not the complete spectrum of the periodic table, just ones that are within a very narrow range. And if you assume that the number of electrons that you're determining can be done to establish the atomic mass or atomic weight of the substance out there, then it is a pretty good estimate of density. And incidentally, it's reported in standard density terms of grams per cubic centimeter or kilograms per cubic meter, not in specific gravity, but actually in physical density. All right? So far, I'm assuming that people have a basic understanding of chemistry, so this is not all that unfamiliar to you. So it's a bulk density measure. And here what you got now is the density thing on one side, and this is gamma ray on the other side. And again, it's important that you link them together. And this is one of those things that you might want to look at later on when you have a chance to. Here you see gamma ray responses to sandstones, then a kick as you get into a siltstone, and then notice how, see, the gamma ray response is actually shifting gradually over towards the sand line. That would imply that you're dealing with a gradual coursing downward sequence, or actually we should say coursing upward sequence. Notice the density response is absolutely consistent because shales and sandstones are composed of siliciclastic minerals. Clays and quartz have about the same specific gravity, about 2.65 or so. But when you start getting into things like coals, you start getting into limestones, then you start seeing shifts in the density because calcium carbonate is a more dense, has a higher specific gravity than quartz does. Here are some of the numbers, okay? So for a quartz-rich sandstone, all right, 2.65 is specific gravity. Coal, 1.2 to 1.8. It's a lot lighter. I mean, I don't have to tell you this. You guys can pick up a chunk of coal. You know, a chunk of coal this big and a chunk of sandstone this big are going to be completely different weights. Halite is about between the two of them. Limestone and dolostone and rock or minerals like anhydrite have significantly higher densities that can be easily spotted on density charts like this, okay? And you can start seeing some combinations of things. Here we see, where's a coal response here? All right, here's a coal response. Okay, we get this big kick over like this, over there. You can see the density is shifted way off to the right-hand side of things. There's a tuff. Tuff bed, in this case, has a real low kick in terms of gamma radiation, or sorry, very high kick in gamma radiation. You can actually see a kick in through here with the density differences. If you know what the types of rocks are in the subsurface you might encounter, by comparing these two as well as other logs, you can get a really good handle on the nature of the lithology that you are dealing with. So it actually is, as I said, if you look at these things in conjunction, you can do a lot more than just trying to figure out whether something might be a sand or a shale. All right, now this diagram up here is just a combination of various things that you don't have to worry about at all. Again, it's up here primarily because I need time to get to the second part of the drawing component for today, which is the responses that you're going to get in terms of some of these logs and why they are important. So, Diane, if I can get you to shift your focus to here now. Lights coming on again. What we're going to be looking at is a combination, or actually just a density log, but here we have calcite, as in limestone, dolomite, as in dolostone, halite, as in halite, quartzarite, shale, and anhydrite. Now, if these are pure substances, when you're looking at it, the density, there's 2.0, there is 3.0, and again, to be consistent, we'll call this kilograms per cubic meter. And incidentally, kilogram per cubic meter is consistent with grams per cubic centimeter, and everyone should know that. All right, so for the calcite component, that's about 2.71. For the dolostone, 2.87. I'm just pulling these numbers out of my ass, so to speak. They're accurate, but not necessarily always the same. For halite, 2.03. For quartz sand, my favorite number, 2.65. For shale, 2.65. And for anhydrite, pretty darn close to 3.0. Now those are the actual densities, and if you're dealing with pure materials more or less stratigraphically on top of each layer, that's what you would expect to see the response for. But in reality, it doesn't quite work that way because there's a certain amount of lag. So your density response may actually look something like this. Now once again, there's two things to consider about this. One is the lag time, the response time that it takes for a probe to actually tell that there's a difference in rock types. That might explain some of this that you see through here. But then you start looking suspiciously at intervals like this. And intervals like this through here. Because what it's telling you is that the actual porosity within these intervals, actually I guess that one is not such an issue. You'd expect that for the shale. But this interval through here. What it's showing you is that the densities that you would expect for a rock for sudden transition is off a little bit. If this were a sharp contact with 100% dolomite, I mean the ship should probably be more like this. The fact that it isn't can be interpreted as meaning that that dolostone is not as dense in this location as you would expect. How do you decrease the density of a rock? Increase the amount of holes within the rock. So there's a potential for porosity here, okay? All right, that's the reason why these logs are called the porosity logs. But they're not going to directly show you where there's hole space. They are interpretive. They are more or less inquisitive. You have to make that determination yourself. Now, I'm going to erase this because I need... I will instead... see if it works with the lights off this time. Oh, damn. All right, hang on a second. It's off? Good. That thing is inconsistent is what the problem is. I want to show you one other important thing here, because we're talking about neutron and density logs today. You should be aware of one of the more important secrets in the oil industry. Combining neutron and density logs together. So this is the last diagram that you have to worry about, okay? It's going to be a quick one. Not going to worry about different types of rock units or anything like that. Two lines. One is going to be the neutron line. Then the second one will be density. In petroleum, one of the things you want to look for is something called crossover effects. Crossover occurs where the neutron and the density curves cross over one another. Gee, what an interesting concept. Notice at this point and at that point. This interval through here is more often than not going to be a gas-filled interval. And in fact, in the oil industry, they actually refer to this first point here as the water-gas contact. Now, depending upon the scale of this particular log, I mean, if we're talking about this being 100, 200 feet, you got yourself a horrendous gas zone. You don't get an awful lot of those in the real world. What you end up getting are small little crossovers that might give you an interval of maybe 20 or 30 feet of potential gas play. All right? So this type of thing is an important thing to look for if you're looking at gas-bearing zones. If there's an unfortunate concept to this now, or an unfortunate problem with it, is that oil doesn't really show you the same crossover effect because, again, it's very hard to resolve water and oil using neutrons. But for gas, it's good. And up until a couple years ago, that was sufficient to get people really excited because, frankly, gas was paying off big bucks. But we're in a situation now where the gas is not so good as a play because we have a lot of gas that we've discovered recently. So crossovers like this giving you gas-filled intervals may not be as exciting as they were because gas just isn't costing as much. It isn't getting as much profit in it as we used to have. Okay? All right? Think you can kill that. And this is the last time the lecture. If you want to see what the real crossover effect looks like in a real log, it looks like this. Okay? So here is a crossover effect. The FDC is the density log. The CNL is the neutron log. All right, and there's the crossover. So there is a gas play zone indicator like so. It's not unusual if you're working in the oil industry when you see these things to color them in red or blue as a potential pay zone. Now, the one thing you should also be aware of is that gas can also be an oil indicator, because gas floats on oil, which floats on water. So if you have this type of crossover, it tells you that there's the potential for strong amounts of gas there. But if the other characterization of the logs indicate that you still have a porous interval, then you still have the potential for having fluids below the gas. If you're lucky, one of those fluids will be salt water. Why would salt water overlain by oil be something that would be easy to spot? What would you look for? Resistivity. You see a sudden drop in the resistivity as you drop from the oil into the salt water, but you would still see characterization in either the SP or gamma ray logs to indicate it's not a shale contact. All right? You see how this all works now? So being asked to correlate rock units is one thing. You can correlate rock units on the basis of an SP log or a gamma ray log or anything like that. But being asked to look for oil or gas requires you to be able to understand how the characterization of the other logs actually works. Which is why when you guys do a cross-section, you don't want to just give me formation thicknesses. You don't want to just be able to present formation thicknesses. What you want to do is be able to present formation thicknesses to give you an idea where there are potentials for stratigraphic or structural traps, and then be able to look at where those potential traps are to say where that might be a good place to drill for oil or that might be a good place to drill for oil. And don't always assume that the most obvious trap is also going to be the place that's going to be the one you want to drill for if the other characterization of the logs tells you there's nothing there. Part 2 of this exercise will throw neutron and density logs at you, where you can start thinking now about the composition of the fluids, not only the formation thicknesses. All right, now with that, we'll call it quits. But before you run off, be aware, next time you meet is an exam. All right, it's your midterm exam, or what will constitute a midterm exam for this class. It will be an in-class exam, closed book study. If you haven't been paying attention to the lectures, all the lectures are online. I would recommend that you go through them again, watch them, and make notes. Also, make sure you download and use the available online resources that are there for you as well. Okay? All right, with that, we'll call it quits. So you have by the way, the lecture that I'm going to be recording with this professional is not going to be something that's going to be on the exam. So you're off the hook for that, even if it comes online before the exam is online, okay? But the stuff we talked about until this time, fair game. In particular, be familiar with all those goddamn acronyms. API, CNLs, I love those acronyms. Oh, I love them a lot. Diane, thank you. I hope it worked.